Hello everyone, welcome back to Abstract Algebra. Today we're going to talk about Cayley's theorem, which is a very important theorem, a theorem by Arthur Cayley, a British mathematician. And it is important because it justifies the statement that is said that permutation groups are very important because what I mentioned is that G is a finite group, then G is going to be found as a subgroup of some permutation group. So that is precisely the theorem we want to prove today, is that every finite group is isomorphic to a subgroup of a permutation group. How are we going to prove this? Let me give you an example first of how this is going to work out, and then we'll do the actual proof. So here's an example. I want to show you how one would find z modulo 3 inside a permutation group. We're going to go back to the Cayley table of z modulo 3, 0, 1, 2, 0, 1, 2, 0, 1, 2, 1, 2, 1 and 1 is 2, 1 and 2 is 0, 2 and 1 is 0, 2 and 2 is 1. And then notice that each one of these rows is, well, they are permutations of the numbers 0, 1, 2 of the elements of z modulo 3. So what do they correspond to? The very first row is the permutation that sends 0, 1, 2 to just 0, 1, 2. The second one corresponds to the permutation that sends 0, 1, 2 to 1, 2, 0. And the third one corresponds to 0, 1, 2 to 0, 1. If you think about these now as the first element, the second element, and the third element, first, second, and third, first, second, and third instead, then we can write them in terms of cycle notation. So this is the identity cycle. This is the cycle that sends 1 to 2, 2 to 3, and 3 to 1. So this is the cycle 1, 2, 3. And this would be the cycle that sends 0 to 2. So 1 goes to 3 and 3 goes to 2. So it's exactly those three elements. So I can actually now write for the time being, a bijection that sends z modulo 3 to the identity 1, 2, 3, 1, 3, 2, which is a subgroup of S3, is the subgroup generated by 1, 2, 3. And this is, in fact, an isomorphism. How do I show that this is an isomorphism? It's certainly a bijection. It's sending 0, 1. It's sending 0 to 1, 1 to 1, 2, 3, and 2 to 1, 3, 2. How is this a bijection? Well, it is a bijection for sure. But how is this an isomorphism? Why is it preserving structure? Well, it is because I can write this in a different way. I can write this as n mod 3 goes to the power of 1, 2, 3 to the nth power. You see that now it does work, that for 0 modulo 3, it goes to the identity. For 1, it goes to 1, 2, 3. For 2, it goes to 1, 2, 3 squared, which is 1, 3, 2. And once I know that, then if phi of n modulo 3 is 1, 2, 3 to the n, then what is phi of n plus m? That will be 1, 2, 3 to the n plus m, which is 1, 2, 3 to the n times 1, 2, 3 to the mth power, and that is phi of n times phi of m. So it preserves a structure, so it is a group isomorphism. So what we've seen is that Z modulo 3 is isomorphic to the subgroup generated by 1, 2, 3 and S3. So we have been able to see that a group is indeed a subgroup of a permutation group. So let's try to carry that idea over to any group. The very first thing I want to show you is that indeed the rows of a Cayley table are permutations of the elements of the group. So let G be a finite group. And let G be in G. Let lambda G is going to be the map that goes from G to G that sends any element A to G times A. So multiply on the left by G. This is what's happening in the Jth row of a Cayley table. If I have the Cayley table and I have G1, G2, all the elements of my group, when I have the G row here, this is G times G1, this is G times G2, and this is G times Gn. So if this map is a bijection, that implies that this row is in fact a permutation of all the elements of G. So this is going to correspond to a permutation of the elements of G, which in turn corresponds to a permutation of the numbers 1 through n, which denote the index of the elements of G itself. So let's prove this. Okay, so first of all, lambda G is well defined. Indeed, if A is in G and G is in G, then G star A is in G because the group is closed. So by closure, that is true. Now, I want to show that lambda G is injective. How do I show that this is injective? So suppose that I have lambda G of A is the same as lambda G of B for some A and B in G. Then what I would get is that G times A is the same as G times B. But then by the existence of the inverse of G, I can multiply both sides by that inverse. And that would imply that, well, if you cancel out the G and the G inverse on both sides, that A is equal to B. And that tells me that the map is, in fact, injective. Let's now show that lambda G is surjective. So how are we going to do this? Let's first think, what do we need? For any B in G, I want some A that is going to give me B. But this is just G star A has to be B, and therefore I want to solve for A. A will be G inverse star B. So let B be in G. Then there is A in G given by G inverse times B. Notice that, well, G is in G. There is an inverse by the axioms. And by the closure, G inverse times B is in G, such that what happens if I send this A, this lambda G of G minus 1 star B, will be precisely G, no parentheses here, times A, which is G star or G minus 1 times B, and this will be G times G inverse will be the identity, and that just will be B. Thus, lambda G is surjective, injective, and a bijection. Okay, so what we have is these lambda G's that just send any A to G times A. Those are bijections. So therefore, every row of a Cayley table is a permutation of G. So now I can actually prove Cayley's theorem. So theorem, Cayley, let G be a finite group. And in fact, I can say a little bit more in the statement of order n. Then there is a subgroup H of Sn such that G is isomorphic to H. So the group G of order n will be contained in Sn. So we'll find some subgroup that is isomorphic to G in there. So how are we going to do this? We're going to use those maps lambda G as before. So let G be a finite group. And I'm just going to write already G as G1 through Gn. This first element will be the identity, but it doesn't matter. I have all the elements. And for G, in G, let lambda G be the map from G to G that sends any A to G times A. Okay. Then this is a bijection by the lemma. And therefore, lambda G is a permutation of the elements of G. So it's in the symmetric group of G, which is the symmetric group on really the letters G1 through Gn, which is just like the symmetric group of the letters 1 through n, which is Sn. Okay, so I'm going to define what is going to be the subgroup. G hat or G bar is going to be all the lambda G's, one for each element of G. Okay, that is my what I'm going to claim that is a subgroup. And notice that this is contained in the symmetric group of G, which can be identified really with Sn through this identification. Okay, the identification being, so this is identified with Sn through, if you have sigma sends Gi to Gj, then we have a sigma here that sends I to J. So that identification, just the ordering of the elements gives you what is happening to the letters 1 through n. So that's how we identify the symmetric group of G with Sn. And similarly, G bar is going to be, for the time being, a subset of the symmetric group of G. So it's a subset of Sn. And what I'm going to do to complete the theorem is to show that this is, in fact, the H that I'm looking for. It's going to be a subgroup. So we claim that G bar, the subset of these permutations of the elements of G, is a group. And in fact, well, it is a subgroup of the symmetric group in G. But let's prove that it is in fact a group. First of all, under composition, this is closed. How so? Suppose I am composing lambda G with lambda G prime. What does that look like? Well, let's see what it does to an element of G, that would be lambda G of lambda G prime of an element A, that is lambda G of G prime A, and lambda G would be G prime A, which is the same as G prime times A, so it is lambda G prime acting on A by multiplication on the left. So therefore, what we have is that this product is lambda G prime, which also belongs to G bar. So it is closed under multiplication, which in this case is composition. Let's see that it is associative. So G under composition is associative. Composition of functions is associative. So lambda G composed with lambda G prime composed with lambda G double prime will be the same as lambda G composed with lambda G prime composed with lambda G double prime. You can see that in both cases, this is lambda G prime G second. So yeah, so it is that function. So we can see that in both cases, we get the same thing. So it is associative. How about the identity? Do we have an identity? Has an identity element, which is namely the identity map, lambda E from G to G that sends any A to E times A, that is just A, that is the identity. And you can see that lambda E composed with lambda G, that will be lambda E times G, which is lambda G, which is the same as if I compose first lambda E and then lambda G, it get the same thing. So that acts as the identity. And finally, I need inverses. Has inverses. Do we? Well, yes, because what is the inverse of lambda G will be lambda G inverse, because this, as we've seen, this is lambda of G inverse, which is lambda identity, which is the identity, and similarly lambda G inverse composed with lambda G, that would be lambda G inverse G, which is the identity. So those are my inverses. So I get the G bar under composition is a group. Is a group. Great. What else do I need to do? I have a group. Now I need to see that actually G and G bar are actually isomorphic. Moreover, G is isomorphic to G bar. How so? We're going to need an isomorphism. Consider phi from G to G bar that sends G to lambda G. Then we want to show that this is an isomorphism. So let's first see that this is injective. So if lambda G is the same as lambda G prime, then, well, in particular, they have to act the same on the identity in G. So they have to have this, but this is G times E, which is G. And on the other hand, this is G prime times E, which is G prime. And therefore, I get the G equals G prime, and that gives me injectivity. So this phi is injective. How about surjective? Surjective, well, clearly, any element on G bar is of this form, and phi of G is lambda G, so it is surjective. So surjectivity comes from for free, really, from the way we defined it. All right. So what do we else do we need? We need to show that this actually preserves the structure, the group structure. So remember, I have this map that sends G to lambda G, and I need to check what happens if I do phi of G times H. Phi of G times H will be lambda of G times H, but by the property we've seen, this is lambda of G times lambda of H, which is phi of G composed with phi of H for any all G and H in G, and therefore phi is an isomorphism. And then we are done because we have seen that for G, a finite group, we have that G is isomorphic to G hat, and G hat is a subgroup of the symmetric group of G, which we have identified with Sn because this is G1 through Gn, and that means that is a symmetric group in n letters. So we have what we wanted. We have shown that we have a subgroup of Sn that is isomorphic to G, which is Cayley's theorem. Let's do one more example. Now, following exactly the proof, just to understand what's happening in the proof, let's show that Z modulo 4Z is a subgroup of a symmetric group. What's going to happen is that Z modulo 4 is going to be a subgroup, which we've called Z modulo 4 bar. Inside, there are 4 elements in Z modulo 4, so it has to be inside S4. What is the map? We're sending classes like Z modulo 4 to the map, the permutation that is multiply or star by 0. In this case, we are under addition, so we are adding 0 to everything. So this goes to the map that sends 0 to 0 plus 0, which is 0. Then 1 goes to 0 plus 1, which is 1. 2 goes to 0 plus 2, which is 2. And 3 goes to 0 plus 3, which is 3. 1 would map to the map that goes 0 is sent to 1 plus 0, which is 1. 1 will be sent to 2. 2 will be sent to 3. And 3 will be sent to 4, which is 0. 2 will be sent to the map that sends 0 to 2 plus 0, so to 2, 1 to 2 plus 1, so to 3, 2 to 2 plus 2, and 3 to 2 plus 3, which is 1, and then 3 is the map that sends 0 to 3, 1 to 0, 2 to 1, and 3 to 2. So you can see that this is as a permutation of the letters 1 through 4, or the permutation of the letters 0 through 1, 2, 3. This is precisely the identity. This is sending the first letter 0 to the second letter. The second letter is going to the third, and the third is going to the fourth. So it's this map or this permutation. In here, the first letter is going to the third, and the second and the third is going to the and the third is going to the first. So is 1, 3, and then the second letter is going to the fourth, and the fourth to the second. And in here, the first letter is going to the fourth letter. The fourth letter is going to the third letter, and the third letter is going to the second letter. So it corresponds to 1, 4, 3, 2. So what we get is, in fact, this group. So this is my H, is the identity 1, 2, 3, 4, comma, 1, 3, 2, 4, comma, 1, 4, 3, 2 as a subgroup of S4. And notice, by the way, that this is actually the cyclic group generated by 1, 2, 3, 4, which is a group that is isomorphic to Z modulo 4. So we do get a subgroup in S4 that is isomorphic to the original group we wanted to realize inside S4. So that is an example of how the proof actually went, and that exemplifies how the proof works. Okay, so next time we'll talk about direct products.